Okay, so we're kind of laying the ground. We're not ready to do a full significant test yet in this section, but we're getting the basics here. So you're going to be almost ready to do one after this lesson. Um, this is the homework. Okay, the claim that we weigh evidence against is called the null hypothesis. So I want you to think of the null as nothing unusual is going on. Like that's the claim, 48% of people drink Coca-Cola in the United States or something like that. Whatever the claim is, there's nothing unusual. Someone says that's the percentage and that's what the null is. We might be trying to prove, I think that's too low. I think that's too high. I think that's just not quite right. There's different ways of saying it, but something called the alternate hypothesis. So you might have an idea like, I don't think that number they stated is actually correct. Let's try to find evidence that is too low, too high, or maybe just not quite right. The alternate, there's two types of alternate. One is a one-sided. So one-sided is when they say, I think it's going to be greater than the null value, or I think it's going to be less than the null value. Two-sided is if they just say words like, I think the true parameter is just different than the null value. So when we say it's different, that just means it might be bigger, it might be smaller, but I just don't think it's right. So two-sided is when you say it's like different, or it's just we don't know which direction, if it's going to be a larger percentage or smaller percentage or larger mean or smaller mean, but we just think it's going to be different. So James is a manager at the Hawaii Pineapple Company. He's interested in the size of pineapples grown in the company's fields. Last year, the mean weight of the pineapples harvested on one of the large fields was 31 ounces. A different irrigation system was installed in this field after the growing season. James wonders if this change will affect the mean weight of pineapples grown in the field this year. What's the appropriate hypothesis for this? So what are we measuring here? So the mean weight of pineapples grown in the field this year. So that's it's definitely mean, not a proportion here. So that's our mean, mu, there. So what is the null? So the null is, so by the way, the notation for this, so let's just kind of, let me just kind of write this out. So mu, the mean is the mean weight of pineapples grown in the field this year. Just stop short there. Okay. What is the null? So the notation for the null, it looks like this. Make sure you always use Greek letters, like, we're going to use like the parameters here. So we think the null, nothing unusual is going on. So in this case, we're going to say something like, let's see, last year it was 31 ounces. So we think the mu is 31 ounces. There's nothing unusual going on. That's the null. The alternate, the ha, that's an A there, a subscript. That's an O subscript. Is the mu is, let's see, so is this a greater than, less than? A different irrigation system was installed. They wonder if this change will affect the mean weight. So they're not stating a direction. They're not really committing to a direction. So I think this is probably not equal to. So this would be a two-sided. If I did this right, it's a two-sided test. So when we say two-sided, we're talking about a normal curve. There's parts over here and parts over here. When we say two-sided, that's what we mean. It's actually going in both directions, but we'll see. And that's exactly what they said. Good. The mean weight of all pineapples grown in the field this year. Good to put the units there too as well. The hypothesis should express the belief or suspicion we have before we see the data. So hypothesis is important. It's a little sketchy when scientists or statisticians say, let me look at the data and then I'm going to come up with my hypothesis. That would be bad, right? We want to do this before we look at the data. Do not look at the data first and then frame the alternate hypothesis. So that's not how we do it. Again, really important. Do you see what it says there? The null is p hat? No, the null is not ever going to be p hat. It's going to be p. Not x bar, it could be mu, right? So we're talking about parameters here. Never define the null or the alternate with statistics. They have to be parameters. It's a really important point, actually. So the p-value of a test is probably getting evidence for the alternate hypothesis as strong or stronger than the observed evidence when the null hypothesis is true. That's the definition of a p-value. So the National Institute of Health recommends a calcium intake of 1,300 milligrams per day for teenagers. They are concerned that teenagers aren't getting enough calcium on average. Is this true? Researchers decide to perform a test, and they say, and does that make sense what they're about to say there? So the null, nothing's unusual. The mean is 1,300. Notice we use mu because it's a parameter. But they think teenagers aren't getting enough. That was their hypothesis before they did any testing or anything or any sampling. So the alternate is definitely less than in this case. That's a one-sided test, by the way. Where mu is the population of mean daily calcium intake for teenagers. They asked a random sample of 20 teens to record their food and drink consumption for a day. The researchers then compute the calcium intake for each teen. Data analysis reveals that X bar is 1198, which is less than 1,300, by the way, with a standard deviation of 411. They performed a significant test, which we don't know how to do yet, but we'll learn soon, and obtained what's called a p-value of 0.1405. So 14% is the p-value there. Okay, so explain what it would mean for the null hypothesis to be true in this setting. So explain what it means for the null hypothesis to be true. So it's just saying if the null is true, then the mean daily calcium intake for teenagers is 1,300 milligrams, right? Something to that effect. The null is, the mean daily intake. That's right. State the evidence for the alternate hypothesis. The only evidence we have right now is that the sample we took of 1198 milligrams is less than 1,300, right? So the evidence for the alternate, is we did take a sample that's less. Now, we'd like to get some percentages or something, well, we have a p-value. That's actually what's going to sway it or not. Interpret the p-value. So one of the things when you interpret the p-value, you have to say, we're interpreting that given or if the null is true, the mean intake of 1,300 milligrams is the daily mean calcium intake for teenagers, then there is a 14% chance so there's a 14% probability of getting a sample mean of 1198 or less by chance alone in a random sample of 20 teens. So that first part's important, assuming that the null is true, assuming that 1,300 really is the mean daily calcium intake, there's a 14% chance or probability of getting a sample mean of 1198 when you take a sample of 20 teens. So that's not that unlikely. We'll talk about how to interpret, how to make a conclusion about the p-value, but similar to what we've done before, 5% is kind of our unusual, level. 14%, not that unusual. I don't think we can prove the null wrong here. It doesn't mean that 1,300 is the daily mean intake there, but it means we can't prove it wrong because 14% is not that unusual. They leave out the statement that the null hypothesis is assumed to be true when calculating the p-value. So that's the main error we see there for sure. The significance level alpha. So alpha is called the significance level, is the value we use as a boundary to decide if an observed result is unlikely to happen by chance alone when the null hypothesis is true. P-value less than or equal to alpha, because the value of the p-value of blank is less than the alpha, which is blank, we reject the null. So usually, almost always, usually the alpha is 5%. That's typically our level for unusualness. So if our p-value is less than 5% is what this is saying. So less than our alpha of 5%, we're going to reject. So if you have a small p-value, less than the alpha, or usually less than 5%, we're going to reject the null. There is convincing evidence for the alternate. And then in context, you talk about the context of the problem. That's typically how we script it here. So if the p-value is bigger than alpha, because the p-value of 14% is greater than the alpha of 5% or 0.05, we fail to reject the null. There is not convincing evidence for the alternate in the context of the problem that that the mean daily input is less than 1,300. In the preceding examples, we had that. What conclusion could you make at the 5% level? Because the p-value of 14% is greater than the alpha of 5%, we fail to reject the null. We don't have convincing evidence, right? Because 14% is not that unusual. That's not convincing evidence that teens are getting less than 1,300 milligrams of calcium per day on average. If you're asked to make a conclusion and no significance level is provided, that happens a lot, by the way. You just kind of assume it's 5%. That's our kind of normal alpha level. Sometimes it changes. We might talk more about that later, but based on what kinds of things you're doing. Sometimes we have to be more careful with medical life and death situations, so we make the alpha level smaller. Sometimes it's more social media stuff, and we can make the alpha level a bit bigger than 5%. So not life or death situations for that kind of thing. Never, ever accept the null. We're not saying the null is true. We're trying to prove the null wrong. If we have a p-value that's really small, we can prove it wrong, but we can't ever accept the null. We just fail to reject the alternate. Like we fail to reject the null, which means, we reject the alternate. Alpha should be stated before the data is produced. Again, the null and alternate and the alpha should all be stated before you start. You can't change the alpha level. Oh, I got a p-value of 6%. I'm going to make the alpha level 7%. So that we have significant results. Axe throwing is being a popular recreational activity. Your friend claims to hit the bullseye, the center of the target, on 2/3 of their throws. You doubt your friend is accurate as they claim. State appropriate hypothesis performing a significant test. Be sure to define the parameter of interest. Right. So for this one, is this a mean or a proportion here? So 2/3. So this seems to be a proportion. So P is the true proportion of axe throws that hit the target. Something like that. So P, so the null, we say the null, is that P equals 2/3, or 0.6667. The alternate, let's see if they stated a direction or not. Make sure, don't use P hat here. We're talking about the population parameters. State appropriate. See, so you doubt your friend is as accurate. So we think it's less than 2/3. See, we don't think he's hitting the target that much, right? So let's see what they said. That's right. Okay, so the Pew Research Center asked a random sample of U.S. parents if they knew their child's cell phone password. It's actually interesting. Of the 1,060 parents surveyed, 52% said they knew the password. Does this sample give convincing evidence that more than half of all the parents know their child's password? A significant test was performed where the null is nothing's unusual, 50% know it. The alternate is we think a little bit more than that, where P is the proportion of U.S. parents who know their children's cell phone password. The p-value is 0.0985. Explain what it would mean for the null hypothesis to be true in this setting. That means, if it was true, that would mean that 50% of parents know their child's cell phone passwords. State the evidence for the alternate. Well, we took a sample, and in that sample, more than 50%, exactly 52%, knew their child's password. Interpret the p-value. So because the p-value of 9.85% is greater than the alpha level of 5%, we fail to reject the null. We don't have enough evidence to conclude that more than 50% of parents know their child's cell phone passwords. Again, we're not saying the null is true. We're just saying we don't have enough evidence to prove that it's not true. Harris poll found that 33% of U.S. residents believe that finding and picking up a penny is good luck. Mr. Tyson suspects that the students at school are more superstitious than the nation and wishes to perform a test. Okay, no. Population proportion is 33% of people think they're lucky when they pick up a penny. Alternate is he thinks more than 33% at his school will do that. P is the proportion of students at Mr. Tyson's school believe finding a penny. From a simple random sample of 100 students, he finds 45 who believe that finding and picking up a penny is good luck. Okay, so the resulting p-value is 0.0054. What conclusion can you make at the alpha equals 10% level? Because the p-value is less than the alpha of 0.0054, is less than the alpha level of 0.1, we reject the null. We do have evidence to say that the students, more than 33% of the students at his school believe that picking up a penny is good luck. That's the lesson for today.